So as I mentioned before, I think they are using pulse frequency modulation to basically just make a tiny little impulse of current into the inductor and out to the output capacitor to maintain a reasonable output voltage. As you saw, it varies a lot, but they do this to save power. So I'm curious to see what happens if we connect, say, a 1 mega ohm load. Right now the only load that's on there is the microcurrent. So let's connect up the 1 mega ohm load. And it does seem to me that the scope updates a little bit faster now. So we might have a more frequent pulse. And yes, we're down to 150 millisecond between the pulses. So let's try a 100k load and see what happens. So I just zoomed in on the pulse again here. Oh, this is interesting. Let's zoom out. So as I kicked the load down to 10k, I noticed that, well, we ain't getting anything on the scope. If I put it to auto, you can see it's basically just at 0. Even if I turn the trigger all the way down. So I thought, well, the microcurrent may have run out of power. So I checked the battery. It wasn't low. Battery OK LED also lit up on the microcurrent, but I changed it anyway. Didn't solve the problem. So I was thinking, what might be the problem? Well, the battery that I'm using is at 1.45 volts. And if we actually measure the output voltage of the Batteriser here, you can see this is also just 1.4558 volts. So it's not regulating, it's just passing the current straight through. There will still be a current draw on the battery, of course, but it's just so tiny that I didn't see it on the microcurrent. I was still expecting the pulses, but let's just do something to get it to regulate. So I got a different one here that I found in the used batteries box. It has 1.35 volts and it should regulate now, hopefully, unless I broke the Batteriser. And sure enough, it's at 1.48 volts now when I use the multimeter. So let's look at the scope. So interestingly enough, it's still pulse frequency modulation. Maybe that other battery was just right on the edge of where it wanted to regulate, or just pass it straight through. It did look like it was going into pulse width modulation though, but apparently not. Let's just try that again. And here back with the higher impedance load, and you can see it's still pulse frequency. Let's drop it a little bit further, now 470 ohm. Should be pulling around 3 milliamps. Still looks like pulse frequency modulation to me. Now I'm using a 220 ohm resistor. Well, maybe still pulse frequency, or just a very bad oscillator and a short duty cycle, but here at 100 ohm we should be drawing 15 milliamps, but it still looks like the frequency goes up. Let's just drop it straight down to 10 ohm, so 150 milliamps now. And I think we finally went into pulse width modulation, and the bandwidth of the microcurrent is probably not enough anymore, because we just see this very fast ripple here. So if we look at the output waveform here, we might be able to see the switching frequency. I'm not entirely sure this would be it, but it looks like we have like 2, 4, 6, 750 nanoseconds between the pulses there, which would be around 1.33 megahertz, so that sounds plausible. But again, someone who has better gear will most likely test this also. So as you can see here on the scope, when we're drawing 150 milliamps, we get around 1.4 volts on the output actually. So it dropped by 100 millivolts. And that is measured directly across the terminals of the Batteriser. So you can see the ground point is right down here. So I'll have to test that a little bit further later on. We'll see how much current we can pull out of this, but it doesn't look promising, because if the voltage of the Batteriser drops to 1.4 volts when you put a load on it, that's very close to their claimed dropout voltage of a lot of products, which would mean that if it draws more than 150 milliamps you wouldn't be able to use the Batteriser anyway. That's something we need to look into. Anyway, I think maybe we should move on to the load testing and see how the output voltage drops and see how much current it can actually deliver. So to test the current output, I'll be soldering another 2 wires to the output of the Batteriser here. And later we may do some efficiency tests where we also need to measure the voltage right on the input. Hence why we got the extra wire here. So to do the output voltage versus current drawn test here, I just soldered what should have been the positive battery terminal to what actually is the positive battery terminal over here with just 1 wire to get the least amount of voltage drop. Not that it matters, but still. And then we have the grounds going directly to the ground. We take one of the output leads, goes to the DC load that I made, so we can draw some current, and also the ground goes back to the ground. Then I'll connect the other lead here to the multimeter and also the ground point, and we can measure the output voltage. So let's put in the battery. This is the one I used before. It has 1.3 volts across it, open circuit that is. So let's put it in. It's funny that the output voltage seems to vary a little bit here. My load draws about 0.5 milliamp when it's not on, and that pulls it all the way down to 1.46. Anyway, let's try and draw some current. Let's just start with 100 milliamps. It drops down to 1.42. Let's go 200. It's down below 1.4. 300 milliamps. It's down to 1.3. Let's just measure the battery for good measure here. The battery is down to 1 volt in circuit here. So that was 300 milliamps. Let's go 400. And we're down to 1.2 volts and dropping. Let's check the battery. Yeah, the battery is down to 0.7 volts. This is not terrific. Let me try and change the battery for a slightly more fresh one. This one measured 1.46 volts open circuit. But it's the same story. Roughly 1.2 volts at 400 milliamps. So here's a slightly better one. It measures 1 volt in circuit, drawing 400 milliamps, and we're only able to boost it up to just under 1.3. And that's measured directly across the Batteriser with the red and the white wire here. so exactly where your load would have been. Just using my finger to feel here, it wasn't getting hot at all. But let's just go back to 200 with this better battery. So it seems a little bit better. Let me measure the battery voltage again here. So the battery is at 1.23 volts, which is well within the usable range, and we're only getting it up to 1.4 volts. It's not that high, considering that Batteroo was claiming that a lot of devices dropped out at 1.35 volts. You would expect it to deliver 1.5 volts, especially when you only draw 200 milliamps. So it has been going at 200 milliamps for about 15-20 minutes now. The battery voltage is down to 1.16 volts, and you can see we have dropped below 1.4 volts. So I think I'll just try this again with a different batterizer, just to be certain that it's not this one that's just faulty. So I'm going to use this one straight out of the box, never been used before, and I'll just solder the wire to the outside here so we can test it. So I got the new batterizer soldered up here, and this time I was as careful as I could be not to overheat anything during the soldering process. Let's see. Yeah, it's the same story. The battery recovered a little bit while it was unplugged, but you can see it drops straight down below 1.4 again. And measuring the battery voltage, you can see it's setting at 1.17. So 200 milliamps. I would have expected a little bit more. So we already looked at a few different output currents and what the output voltage was, but now let's find out what the maximum output current is, if there is one, and let's see if we can overload it, and let's see what will happen. I'm connecting the battery straight to the batterizer to have the least amount of voltage drop. So I'm not monitoring the input current. That will be higher than the output current, of course, but we are not really interested in that. Then I measure the output and input voltage to the batterizer, and I measure the output current on the fluke here, and then I'll use my DC load to set the current. So this is at 100 milliamps, and I'm using a fairly good battery. It's not new, but it's not completely dead either, and we can repeat the test with a worse battery if needed. Perhaps we should start with a slightly worse battery actually, and then we can put in a better one and compare it to that. So I just put in a bit worse battery, and you can see it hasn't quite stabilized yet on the input voltage, but you can see the output voltage is a little bit lower. It's 1.4 volts, and we're only at 100 milliamps. This is what I really don't like about the batterizer, because it's supposed to be keeping the voltage at 1.5, but let's increase the current and see what happens. Let's just go straight to 500 milliamps, because we've already done that before. And as you can see here, it's basically useless. Let's do the same test with a little bit better battery. So you can see with a half decent battery it's not that bad, but once the voltage drops below the 1.9 or something, it really kills the output voltage. But here we're doing quite well. So will it do 700 milliamps? Yeah, it's not that bad. About 1 amp. Yeah. There's no smoke yet, at least. Let's just let it run and see what happens. You can see as we get down below 800 millivolts, it really kills the output voltage. So just feeling the top of the batterizer here, it doesn't get significantly warm at 1 amp either. You can just feel that there is a little bit of warmth, but it's not hot in any way. But it does boost the voltage a little bit here at 1 amp, but I think we can do better than that. What about 1.2 amps? Nope. It cut out. You can see now the output is less than the input. How about 1.1? Yeah. It sorta kinda works, but it's dropping very low now. We only gain about 170 or 160 millivolts. So no, basically it's not working at 1.1. So 1 amp is basically your maximum current. What if we put in a dead battery? Nope, then it won't do. It won't do anything. But as you can see, you gotta have a fairly fresh battery to draw 1 amp. If we get a slightly more used one, even though the input voltage is higher, it doesn't regulate, and we're still pulling an amp. But if the voltage initially is a little bit high, you can see now it dropped down, then the converter will start up and it boosts the voltage. So let's see what happens if we put a heavy load on it. We know that it won't regulate. Let's just see if it will survive. So we have about 230 millivolt difference at 1.6 amps. So that's a few hundred milliwatt dissipation in this tiny chip here. And now it is getting hot. Pretty hot. I put the load at 3 amps and we're only getting 1.6, so it's basically short circuited. So my battery and the wires are still fine, but the batterizer is getting up to I would say maybe 50 degrees Celsius. But of course it's not a true short circuit because my load won't go any lower. Let's just make a true short circuit. So basically as good as I can make it with these wires. So we're dissipating more than a watt in this now. I don't think I should touch it, but I'm going to do it anyway. Ouch! Yeah, that's hot. Something starts to smell now. So it doesn't look like there's any real short circuit protection in that, but again, if you short circuit the battery, that's not a good thing either, so at least you get a little bit of resistance here. So let's see, it smells like burnt plastic now. Let's see if well, it looks like it's still working. And it looks like it still works. We have 100 milliamps. It's regulating to 1.42 volts. And we have an input of 1.23. So let's try to find the dropout voltage here at 20 milliamps. I'm using a power supply now, and we are supplying 1.6 volts. We get the same out. And if we drop this down to 1.5, we still have 1.5, of course, 1.4. We can accept that. 1.3. Yeah, it's dropping, but it's okay. 1.2. Yeah, it's lower than I would expect it to be, but so 1.1, and it's dropping even further. At 1 volt we're at 1.34. It's not terribly good if you consider it, because in their own videos they said that some products had a dropout of 1.35, I think. maybe even 1.4, and this is this is clearly below that. And at 1 volt there will still be energy left in the battery. If we go to 0.9, that drops below even 1.3, 0.8, and we're down to 1.2 volts. It is still boosting it a little bit though, so in a good product you would still be able to use it. 0.7, it still works, but of course the voltage is low. 0.6, still working a little bit. Let's go 0.55. Yeah. Nope. Doesn't work at 0.5. Let's see when it will start up again. So it looks like 0.7 volts it will start working, and it will drop out at 500 and about 550 millivolts, which is fine because the battery is completely dead anyway. What's not fine is that the output voltage drops as the input voltage goes down. Now most products work down to about 1 volt, 0.9 volts from my experience, but what they claim is that a lot of products drop out at 1.3 or 1.35, which I haven't been able to find any basically that does that, but if it did, then they would only be able to drain the battery down to 1 volt, which would mean they're still not using all the power. At 0.9 or 1 volt the battery is, that's not much, maybe, I don't know, 10%. I'm not sure about that, but you can look up a discharge curve at this sort of current. But so let's try and calculate the efficiency at a few different currents here. So for this we'll be using 4 multimeters. The 2 up here will measure the output. We know that it's going to be 200 milliamps, even though the load doesn't show entirely accurate on the readback. It is 200 milliamps. That is actually pulled into it. And the input voltage and current will be measured by these two. And it looks like my battery is running low. Would you believe it? So I'll just go and change that before we do the test, of course. So I think we're about ready here. Looks like a mess, but we have all the connections to the ground here. We have the input voltage to the batterizer here. The input current is fed in through here. We have the output current through this lead here, and we measure the output voltage. Both input and output is directly on the terminal, and also the grounds, all the grounds are directly on the ground of the batterizer. So let's turn on the load here. We're drawing 200 milliamps exactly, even though it says 197. We can measure the input current here and the input voltage. We will wait until this stabilizes, and then we will note down all the numbers, and we can calculate the efficiency. If we should do this properly, we would use a power supply as the input so that the voltage is nice and stable. But here we're using the product as it is intended with the battery. So it looks like it's almost stable here, so I'll note down all the numbers and we will calculate the efficiency. So if we take the numbers here, the output power divided by the input power, we get the efficiency, which is 91.6%. It's not that bad actually. Let's just do the same test at 100 milliamps. So I think it's settled down here, so I'll note down the numbers. So almost the same at 100 milliamps. It's 89.4%. And at 50 milliamps we're at 87.1%. I wonder what happens if we go up to 300 then, because it seemed more efficient at 200 milliamps. And at 300 milliamps we're actually up to 93%. So let's let's push it 400. And the battery is just dropping right down, but it should still work. Let's just wait a few seconds and see if it will stabilize. So I just did 2 measurements here at 400 milliamps, and one was 91.94, and the other one was 91.5, so very close to 92% again. So here at half an amp, and we have a very significant current going into the Batteriser here, 1.1 amp. But look at the output voltage, it's useless. So at 500 milliamps the efficiency is down to 70.5%. So I'll try to do an ultra low power efficiency test here, where I'm using the watch again. I'm monitoring the output voltage on this multimeter here from the Batteriser, and the output current on the Fluke multimeter. And then down here we're measuring the input voltage and the input current. You can see the battery is 1.26 volts, so it's basically completely dead, as this would be basically the open circuit voltage of the battery. It should have, I don't know, less than 10% of the capacity left, I think. You can see the input current is jumping up and down a little bit, so I'll have to use the Fluke to get the average current of that. But we can see it right here. I'll note down the numbers, and then we will measure the input current with the Fluke. So I think we can take that as 81.8. It goes up and down a little bit, but let me just wait. Well, let's just say 82. So I got the numbers here, and the efficiency is 68% when you're using a ultra low power. And remember, just for the Batteriser to keep itself alive, it needs 16 microamps. Of course, when we have a load, a bit of that energy will go in to powering the load, of course. I did the same test earlier and I got just over 66%, so it is right around this figure here. So I was about to say, let's measure the quiescent current of the chip, because when we put in a new battery, the converter must be totally off. But it appears that the current draw is not much less than when we use a half-dead battery. With a completely new one, you can see it's 15 microamps. We got 16 microamps with a reasonably used battery, and let me just put in a completely dead one. Completely dead in terms of capacity, that is. It still has 1.26 volts on it, but it's basically dead. And you can see here we're only using just over 17 microamps. So there's really no difference.